A hypothesis on the explosive transformation of mass defect in nuclear reactions. Joseph George. Abstract. This paper introduces a hypothesis that the mass defect in nuclear reactions undergoes an explosive transformation into an extremely fine form of matter, driving the rapid acceleration of reaction products. Observed mass defects in astrophysical events, such as stars, supernovae, and neutron star collisions, suggest that space is permeated by this fine matter. This medium could offer alternative explanations for relativistic effects like length contraction and mass increase with speed, challenging the conventional mass-energy equivalence principle and aspects of special relativity. A theoretical model is proposed to explain the distribution of kinetic energy in reaction products. The hypothesis has implications across nuclear physics, astrophysics, and cosmology. Introduction. The mass defect, a central concept in nuclear physics, explains energy released in nuclear reactions and has traditionally been interpreted through Einstein's mass-energy equivalence principle. In atomic nuclei, the mass defect arises because the observed nuclear mass is less than the sum of its protons and neutrons. This difference links to binding energy, which holds the nucleus together and is proportional to the mass defect. This relationship is key in nuclear fission and fusion, where changes in binding energy lead to significant energy release. For example, in the fission of uranium-235, energy release corresponds to the mass defect between reactants and products. In deuterium-tritium fusion, a similar process occurs, where energy released aligns with a small mass difference, illustrating how nuclear energy changes manifest. Special relativity and the mass-energy equivalence principle further connect mass with energy, treating time and length as variables that change with an object's speed. The principle, partly validated by the Michelson-Morley experiment, predicts time dilation and length contraction for objects nearing the speed of light. This theory rejects the concept of ether or any pervasive medium through which light travels, positing that light speed remains constant across all reference frames. This study suggests an alternative view, that the mass defect does not directly convert mass into energy but instead transforms explosively into an extremely fine matter. This explosive process, rather than mass energy conversion alone, could account for the kinetic energy of nuclear reaction products. Observations of high kinetic energies in emission patterns in fission and fusion suggest an explosion within the nucleus, indicating that the missing mass undergoes a phase change to fine matter, releasing energy as kinetic motion. The hypothesis extends beyond nuclear physics to suggest that mass defects across the universe contribute to a fine matter filling space. This matter could interact with moving objects, leading to effects like length contraction and mass increase traditionally explained by relativity. As massive bodies may attract this matter, its density would decrease with distance, creating a medium that could explain the speed of light's consistency around massive bodies and phenomena like gravitational lensing. Methods. We analyze high kinetic energies, back-to-back emissions, inverse mass-velocity relationships, and recoil effects in nuclear fission, comparing these with explosion dynamics. In spontaneous nuclear fission, reaction products exhibit patterns similar to those expected from a localized explosion, aligning with the idea of an explosive mass defect transformation. This explosive process could explain how the mass defect translates into kinetic energy for reaction products, which we evaluate through their behavior in directional emissions. Modeling. The hypothesis further suggests that a universal fine matter medium could interact with fast-moving objects to create relativistic effects. High-speed objects may experience drag from this medium, generating pressure that leads to length contraction and mass increase, effects observed as objects approach light speed. Unlike special relativity, which treats these as geometric changes, this model attributes them to physical interactions with fine matter, offering a tangible basis for these phenomena and establishing a natural speed limit. Experiment idea. To test this hypothesis, californium-252, Cf252, could be used due to its alpha decay and fission properties. By immersing Cf252 in purified water and observing disturbances, including molecular motion or shock waves, we could identify responses incompatible with conventional decay. Sensitive cameras and sensors would capture molecular behavior, particularly motions unexplained by alpha particles or fission fragments. Any consistent, reproducible anomalies could support the proposed explosive transformation of the mass defect and provide new insights into nuclear energy release mechanisms. Results and discussion. Results indicate that high-energy patterns in spontaneous nuclear fission align with the explosive mass defect hypothesis. Observed fragment kinetic energies in back-to-back ejection patterns support explosion dynamics, where the lighter fragment gains higher velocity, aligning with established fission observations. Recoil effects and neutron emissions further reinforce the notion of an explosive process, rather than a simple mass-to-energy conversion, as a primary source of kinetic energy. The model also offers an alternative explanation for relativistic effects, proposing that the drag force from fine matter produces a universal speed limit. Additionally, length contraction and mass increase may result from physical compression and fine matter accumulation. These effects parallel those predicted by relativity but arise from interactions with fine matter instead. While Coulomb repulsion explains some fission characteristics, this hypothesis suggests that the explosive transformation of mass defects provides a feasible alternative for observed dynamics. The model's approach to relativistic drag and mass increase also offers an intuitive framework, challenging geometric interpretations while aligning with current experimental data. This model further suggests that high-density regions around massive celestial bodies might influence light speed, impacting gravitational lensing and photon frequency shifts traditionally attributed to spacetime curvature. Though initial findings align well with the hypothesis, the fine matter model requires further experimental validation, especially to distinguish its predictions from those of special relativity. Conclusion. This study presents consistent evidence for a new interpretation of nuclear fission and relativistic phenomena based on the explosive transformation of the mass defect into ultrafine matter. The model explains key observations in nuclear reactions and relativistic effects through a unified mechanism that provides a physical basis for drag, mass increase, and length contraction. By challenging traditional views, it paves the way for unifying nuclear and relativistic physics through a common framework grounded in mechanical interactions with fine matter. The proposed model requires experimental verification, with particular focus on high-energy regimes where it diverges from relativity. This approach opens new research directions, offering fresh insights into nuclear energy release and relativistic effects. The full paper can be downloaded from the provided link.